Welcome back. The purpose of this particular video and videos like these in the future would be to answer the questions that many of you had during the course of the week. Okay. Now, I felt it's important that at the end of the week I come back and provide a summary video where I might re-emphasize and re-explain a couple of concepts, and in the process I also answer couple of your major questions that you had. All right. Now I have chosen 5 compounds. However, you only see 3 on this particular screen because I want to make it as 2 separate videos to keep the content within 10 minutes of recording time. Right. Now, the first compound, you see the compound has a negative charge. So I'm going to actually write the statement here. Okay. Negative charge, okay, is equal to a double bond. Okay, I'm going to reduce the size here. Okay, okay. Okay. All right, a negative charge is equal to a double bond. Now, what does that mean in case of our Huckel's rule? Now, we already have 2 pi bonds, and then the negative charge is equal to another double bond. So that means now we have 6 electrons total, right? So that means it satisfies Huckel's rule. And I said a negative charge is a double bond. So we have double, single, double, single, double, single. So it satisfies the condition for planarity, and we also have a ring. So this molecule is aromatic, right? So how do we go about moving the bonds around? Now, I always prefer to start with the negative charge. Now, it doesn't matter whether you want to go in the clockwise direction or the counterclockwise direction. Let's go with the clockwise direction first. So you bring the negative charge in, make a bond, and in the process, this bond doesn't go here. Instead, it comes out and goes to this carbon as a negative charge, which you will see in this next resonance structure. Now, resonance structures are indicated by a double-headed arrow. So, this bond is now come here. This is now come here as a negative charge. Let's continue it. So this negative charge now comes here, makes a bond, and this now comes out as a negative charge. So if we continue this process, I'm just going to probably do this in a different color. Okay. You don't need to indicate the lone pair every single time. A negative charge is by default means you have a lone pair of electrons. So the bond has now come out as negative charge. Negative charge is now here as a bond, and this bond is here. Now we can continue this process. This now can come in, make a bond. This can come out, make a negative charge. Now all this has been explained already in the previous content videos, but sometimes, you know, when you say the same thing the second time around, I think it seems to make more sense. There you go. I already have, you know, this is a structure. Since, I mean, resonance structures mean they're all resonance structures. So we have 4, and you can keep going, and eventually you will end up where you started. All right. So that's how you handle a compound with a negative charge. Now let's go and handle a compound with a positive charge. Okay. Now, is this compound aromatic? Well, it's 4n plus 2, right? We have 2 2, and 4. Unlike a negative charge is a double bond, a positive charge does not mean anything. It just means no electrons. That means we only have a total of 4 electrons, and there is no way you could get 4 out of 4 and plus 2. So this is not aromatic, right? So there's no need to draw resonance structures. Now, this is very important. I think this was one of the major areas that many of you had trouble with. All right. Now, this is important from a test perspective too. Okay. Now, nitrogen can only have 3 bonds, and when it has 3 bonds, it has a lone pair of electron. Whether it's on the inside or outside, we'll look at it at a separate case. But nitrogen can only have 3 bonds and a lone pair of electrons. Or nitrogen can have 4 bonds, but it must have a positive charge. Now, plus is same as +1, okay? In some cases, you might see people say +1. Some people write just plus. They both mean the same. So this is called a tertiary amine. That is, a nitrogen attached to 3 bonds is a tertiary amine, whereas a nitrogen attached to 4 bonds and a positive charge is called a quaternary amine. Keep in mind, these two concepts are very important from a test perspective. Okay, this is a tertiary amine, this is a quaternary amine. Nitrogen can only have 3 bonds, and if it has 3 bonds, it can have a lone pair. If nitrogen has 4 bonds, then it must have a positive charge, and it is known as a quaternary amine. Now, a plus charge is same as +1, okay? So if you see a +1 on a test, you know it's same as plus. All right, now the lone pair is on the inside if there is no double bond right next to the nitrogen on either side. And you see there is no double bond here or here, so the lone pair is inside. Now, how do we commence doing the resonance structure? It's very, very simple. I always start moving the lone pair first, okay? So I move the lone pair here. Whenever you're dealing with lone pair, you're not going to just move the bond here. Instead, you will see why, okay? The bond comes outside, okay? So what does the resonance structure looks like? Okay, I am going to redraw everything. Sorry if my hydrogens are a little slanty. Okay. Now, because this element has lost electrons, of course, it's made a bond here. But keep in mind, this electron is lost, so it gets a positive charge. Why? Because the nitrogen, there's 2 ways to look at it. First, the electron is used to make a bond. So this element has lost electrons. In chemistry, whenever something is lost, it gets a positive charge. That's one way to look at it. Or, I just told you, this nitrogen now has 1, 2, 3, and then the 4th bond is with the hydrogen, so it must have a positive charge. Okay? And because we have a positive charge, normally we should also have a negative charge, which in this case is because this bond has now come inside to this carbon, so that's a negative charge, and this bond stays here and it's undisturbed. Okay, now I'm going to get a different color to redraw this. Okay, now what can we do? This positive charge stays there, it can't go anywhere else. So just like the previous case, the negative charge now comes in, makes a bond. This, however, cannot go to the next spot. Instead, it comes back to this carbon. So what does that mean? Okay. Now, I want you to think critically because you watch the video 200 times, unless you actually understand what's going on, chances are you're going to keep struggling. Okay, now it's negative. Now this can come over here. Okay, I'm going to do this once because I think this is where I want to stop this video because I don't want it to get too long, because you kind of get the idea. Now this, sorry, this negative charge now goes in as a bond here. And of course, you cannot move the positive charge on the nitrogen. Instead, this comes out and goes to this carbon, makes a negative charge. So what does that mean? Nitrogen, hydrogen. So this will be negative here, positive charge. This has now come as a bond here, and this bond stays here. Again, you can move this inside, and this comes out here, and the negative charge will come over here. So if you keep doing this, eventually you will end up where you started. Okay, at least at this point now we have 4 resonance structures. Okay, but I'm not going to continue doing all of the remaining structures. I want you to see if you can continue where I stopped. This is where I stopped, right? For this, right? You can continue this process. Okay, eventually you can move the bond into the nitrogen, and the positive charge would be replaced by your lone pair of electrons. Okay, just give it a shot. All right, I think I have worked it out in one of my videos, the entire cycle of the compound, but here's where I'm going to stop this. Okay, so now you know how a negative charge works and how a positive charge works. Now I'm going to show you a different compound next time that has a positive charge, but it happens to be aromatic. And what do we do then? All right, so stay tuned for the second summary video.